All right. So I love this stuff. To me, when I think about discrete math, I think about graph theory, and trees are a type of graph theory. So we'll first learn about the vocabulary with graph trees, and then look at how to search a tree, so more of a programming aspect, and then minimal spanning trees. That's kind of our goals. So just some terminology. When you have a tree, they have different levels. So this is level 0, level 1, level 2, and level 3. So the only vertex at level 0 is 6. Both 2 and 8 are considered level 1. 1, 4, 7, 9 are considered level 2, and so on. Descendants are just think about like a family tree. They're the ones that descend from that. So the descendants of vertex 2 would be all the ones attached below it. So 1, 4, 3, and 5 are all descendants. Siblings are, again, what you think of. If 2 is a parent, the siblings would be 1 and 4. So a sibling is someone who comes from the same parent. So it's kind of a mix of family trees and then literal trees. So the word leaves are all the ones at the end. So like all the branches, but the leaves. So here the leaves are 1, 3, 5, 7, and 9. They are all, there's nothing below them. They have no descendants. And the height of the tree is, how many edges to get from the top to bottom. So there's 1 edge, 2 edge, 3 edge. So there's 3. The height is 3 because it took 3 to get from top to bottom. It's all the same. If you have all the different levels, it's the highest level. And then an end tree is, well, let me label these. The number of descendants on 6 is 2. The number of descendants on 8 is 2. This is 2, and 4 is 2. So look at all the vertices that have descendants, and if you label number of descendants, that'll tell you whichever number is highest. So here they are all 2, so this is a 2 tree, and it's actually a complete 2 tree because they are all 2. If I had one more edge coming off of 8, so that this was no longer 2 but 3, then it would be a 3 tree but not a complete 3 tree. Any questions on the terminology? Okay. So any algebraic expression can be written as a tree. Oh, good, Thomas. I like that you like it. And then the way we're going to think about it is whatever operation would be last goes at the very top. So if you think about what you would do first, kind of the 2 and 7, maybe the 3 and 11 first, then this plus x, then this divide by y, then this division is last. So that's what's going to go at the very top of the tree. So the two things that you are dividing are this one huge expression, the 2 times 7 times plus x divided by y, and then you also have 3 minus 11. So then you think about within each of these, what is the last operation you would do? So I'm going to do the right side first because it's easier. In the 3 minus 11, there's only one operation. So let me erase the 3 minus 11 and put the tree there. So the tree will have the operation. So the operation is the subtraction. The two things I am subtracting are 3 and 11. Looking at this expression, the last thing I would do, so again, the first thing is the 2 times 7, then the plus x, divide by y. So the last operation is the division. So I'm going to use division here. And the two things I'm dividing are, this expression, 2 times 7 plus x. Now let's think about this, the 2 times 7 plus x. The last operation would be the plus. So let's take this out, and we're going to put a plus. And the two things I'm adding are an x and the 2 times 7. Alright, so now I'm going to make the 2 times 7 a tree. So the operation is multiplication. I'm going to write multiplication with the star. And the two things I'm multiplying are 2 and 7. So that is my algebraic tree for that expression. Alright. To search trees, there's there's three different kind of search methods. There's this pre-order. So pre-order is node or vertex left, right. So you start at the top, and I go to my node first, so that's A, and then I'm going to go to the left. And I hit B, so B is my next vertex. From B, I'm going to go left, and I'm going to hit D. Well, from D, I can't go left, so I'm going to go back up to B, and I'm going to go right. And when I go right, I hit E. And from here, I can go left or right, but the search says I go left first, so I'm going to go H, and then I. And now I've just done this entire half of the graph. So now I'm going to go right of A, and I get C. And if I go left from there, I go F, and then G. So the order in which you search this graph would be A, B, D, E, H, I, C, F, G. Questions on the pre-order? I just don't want to waste your time. Okay. So in order search is left, node, right. So again, you think about starting at the top, but I can't start there. I need to go all the way left. So if I go all the way left, I'm at D. And then it says, so I went left, all the way left. Now I'm going to go back up to my node, so to B, and I'm going to go right of B. But when I go right of B, I have a new tree. So again, the tree says left, node, right. So on this little mini tree, I go left, which is 8, node, which is E, right, which is I. So now I've just done the left of B. Let me use a different color. I did the left of B, then I did B, and then I did the right of B. So all of that is the left of A. So it's all this stuff on that side. So I did left of A, so now I'm going to go back up to the node. So I did left. Let me kind of write this down. Left of A. So now I'm going to go to node, which is A. And now I'm going to go right of A. So if I go to the right, I have this tree, and I need to go left, node, right. So left is F, node is C, right is G. So if I'm doing an in-order search, it would be D, B, H, E, I, A, F, C, G. Alright, the last search method is the post-order search, and this is left, right, node. Alright, so just like before, I'm going to go left, which is all the way left, so I have a start with a D. So D is the left of B. Now I'm going to do the right of B. But when I go to the right, I now have a new tree. So I do left, right, node. So it's left is H, right is I, node is E. So I did the left of B, the right of B, come back to the node B. Now I just did the left of A, and then I'm going to do A, sorry, not A. Next I'm going to do right of A, and then the very last thing I'll have is A. So if I go to the right of A, I'm left, right, node, so it'd be F, G, C, and now I have A at the end. Alright, questions on any of those search methods? Okay. Alright, so the minimal spanning trees, the idea is you want to span the entire tree, which means you want to touch every vertex, but you want to get there in the smallest weight. So on the other examples, or other trees that we had, the edges did not have weights, and now they do. So in real life, these graphs might represent flights. So the vertices might be airports, and the connecting lines between them might be, would be the actual, flight path, I guess, but with the distance. So a lot of times it's used in traffic situations. So you want a minimal spanning tree means you want to be able to reach all of the hubs or reach all the airports, but in a minimal way. So here are just some examples. So looking, notice here the edge weight is 2. Here the edge weight is 2. I could have taken this 3, but that would have cost more. So again, sometimes cost more maybe in miles, and maybe cost more in another way. So there's 2 algorithms that we do in this class to find minimal spanning trees. So one thing that is I think students sometimes forget is that if you are finding a minimal spanning tree, the weight of any, back up, there's not necessarily a unique minimal spanning tree. There could be more than one, but what's always true about a minimal spanning tree is that it's going to have the same weight as any other minimal spanning tree. So in the homework, you're asked to find the minimal spanning tree using both algorithms, and oftentimes students get different weights, and that's a key indicator that something's wrong. So just use that as a way to check yourself. Alright, so Prim's algorithm is more locally based, so you start somewhere and kind of traverse around until you touch every vertex in some way. What vertex would you guys like to start at? In the recorded webinar I start at 8, but we can start anywhere if you want to see something different. Okay, do you want to start at 8? Alright, so if we start here, we choose the smallest weight. So the smallest weight is this one. So the first edge that we would pick is AC. And then you look all around of all the edges that are touching the edge that you have. So I have a 3, I have a 5, I have a 4, and a 7. So of those 4, we picked the smallest. So the smallest is 3. So my next edge is CG. And now I have the choice of 3, 5, 5, 4, and 7. And again, the smallest is 3. So in this example, notice we're just kind of following along, but it doesn't have to, it could kind of back up and go a different direction. Alright, so the next one is GJ. because that has the minimal weight, GJ. And then from here, again, my choices are 8, 4, 5, 5, 4, 7. I have a choice. So now you can see that they're not unique because I can pick whichever one I want. Which one do you guys want to pick? No. Is there no? Like you just see who's touching any of the edges that you have and you pick the smallest. So I feel like people feel like they're backing up because you kind of feel like you're walking along this path, but you can go from anywhere, whichever one has the smallest weight. Hope that makes sense. Okay, do you want to pick JH or AD? AD, okay. Alright, so what's the smallest weight now? Like what's the smallest weighted edge? DH, good. So DH. Now can you tell me what the smallest weight is? Kind of a trick question. Great. Yes, that's what I meant by kind of a trick question. So yeah, you said HJ, but you can't use HJ because a tree does not have a loop. So if we chose JH, we would close a loop and it's no longer a tree. So yes, HE would be the next one. So HE. And then keep going. EI, awesome. You guys are doing great. Next. IF. Alright, so just looking around, make sure we understand the possible choices that we could take, or possible edges, would be 8, 9, 7, 7, 5, 6, or 7. So the smallest weight here would be the 5, so I'll pick BF. Now what? Great. So FL is one option. So the choices we have are 8, 9, 7, or 7. So we have a choice between KI and FL. So either one. So we'll say FL. And then the only vertex we have not touched yet is K. So to get to K, the least weight would be this 6. So the last one would be LK. And that is our spanning tree. Questions on that? All right. Yes, so what I forgot, or what I need to do now, is look at what the weight is. So I just says use Prim's algorithm to find the minimal spanning tree, but really we want the lowest total, the lowest weight. So, you know, this is a 1, 3, 3, 4, 2, 5, 3, 4, 5, 7, and 6. So if you add all that up, you'll get your weight, and it will be the minimal weight possible that touches all the vertices. Alright, so let's look at Kruskal's algorithm. And Kruskal's algorithm is more of a global point of view. It looks at the whole graph and just picks the edges with the lowest weight. So the edge with the lowest weight is AC. So we're going to start with that one again. And there's no other ones with a weight of 1. So it has a weight of 1. And then I'm going to look at the whole graph, and I find this DH has a weight of 2. And then I want the ones with 3. So I tend to put little curly braces for the ones that the order doesn't matter. So it matters that you choose AC first and DH second, but the next 3 can be in any order. So CG, GJ, and EI, because they all have a weight of 3. Alright, so now I want to use the weight of 4. I have choices again. I need to pick either JH or AD, and just because we picked AD last time, I'm going to pick JH this time. JH, and what is it? IF. So those are weight 4 each. And then I want weight 5. So again, you might be careful not to create a loop. So I have 2 5s, EH, and BF. Now I want a weight of 6. So there's 3 with a weight 6, but 2 of them are going to create loops. So the only one with a weight 6 is going to be KL. And I want you to notice right now that all the vertices are being touched, but it's not a tree. Do you guys know why we don't have a tree yet? Great, it's not connected. So I just need one more edge to connect that KL to the rest of it. And it doesn't matter which one you pick, so I'll pick KI. And so this was 7, this was 6, and 5. So if we add up 1, 2, 3, 3, 3, 4, 4, 5, 5, 6, and 7, you'll get the minimal weight, which will be the same as the weight we found using Prim's algorithm. Alright, so a binary positional tree kind of lines up the different levels. So you'd have 6. So kind of going down this way. You'd have level 0. And then now these will be my level 1 vertices. So I have a 2 and an 8. So level 1's kind of go down that track. And then level 2. So level 2 would be 1 and 4. But on next to 8 you'd have 7 and 9. I guess I should put these little arrows on it. And then level 3, 1 doesn't have any level 3s, 4 does, so it would have a 3 and a 5. 7 does not, 9 does not. So that is the binary positional tree for that graph. I feel like I just flew through that. I really think about it as doing those diagonals by the level.